what gets really interesting, and this is something most scientists don't even know about yet, is level 3, the deep layer of aging. There's actually a DNA clock that tells our bodies how old we are. I could take your blood and read it, and I could tell you roughly when you're going to die. There's a list, a long laundry list. And most of the people in my field have said, okay, we've figured out aging. We've got this list, we put it in a nice pie chart, and that's it. But what I'm saying is that why does all that stuff happen? It's not enough just to tick off what happens. You have to understand, is there an upstream cause of all of that? And so in my book and in scientific papers we are now putting out for the scientific community to read as well, what we think is going on is that our bodies are losing essential information as we get older that drives many, if not all, of those hallmarks that we know exist.
Imagine a world where the aging process isn't inevitable, but something we can control, something we can slow down or even reverse. Harvard professor Dr. David Sinclair, a leading expert on the science of aging, believes that moment is closer than we think. At the heart of his research lies a groundbreaking discovery. Aging isn't just about the passage of time. It's a process tied to the health of our DNA, the way our cells repair themselves, and how we live our daily lives. What you eat, how you exercise, even how you handle stress. These simple choices can determine whether you thrive or deteriorate as the years go by. But it's not all simple. Dr. Sinclair explains the cutting-edge science behind epigenetics and how reprogramming our cellular clocks could unlock decades of healthier living. He reveals practical strategies like fasting, cold therapy, and supplements that could make a real difference in your life today. Of course, these advancements raise big questions. Are these techniques only for the wealthy? What are the ethical implications of trying to reverse aging? And, most importantly, is this science ready for everyone? Or is it just a promising dream? Today we'll explore the groundbreaking research, the practical tips you can use right now, and the debates surrounding the future of longevity. Whether you're a skeptic or someone looking for answers, you won't want to miss this. Enjoy this clip as we dive into the real science of staying young, featuring insights and discoveries from one of the world's leading voices on the subject. Don't forget to like, subscribe, and leave a comment if you enjoyed this video. It's the only way we can know you want more content like this, and it helps us a lot with the YouTube algorithm. Thanks for your support.
So in what way is the epigenome involved in this? How are we losing the information? Give people a quick little diatribe about the difference between genetics, which I think they get, and then the epigenome and epigenetics and how that plays out.
Yeah, for sure. It's not that complicated. There's really just two main types of information in our body that we get from our parents. The first is genetic. We all know about DNA and the 4 letters, A, T, C, G. It's a long molecule in the cell, and it's a string of letters. That's digital. That's like the music that's on a DVD, those things we used to use to store movies. But there's another level of information that's above that in the cells, which is the reader of the information. That's called the epigenome. And that really is different because it's analog information, in the same way that records and cassette tapes. They sucked. They were terrible at storing information. But the problem is we have an analog version of information, the epigenome, which controls which genes in the string of DNA are turned on and off.
And why are you considering that analog? I don't think I understand how it actually works. Like, I can imagine DNA sequences as just sort of repeating the ATCG code, but what is analog about the epigenome? This, reading about it in your book, is the first time that...
So, what can we actually do to slow aging? Dr. Sinclair points to some practical interventions that don't require futuristic technology. First, fasting. By giving your body a break from constant eating, you trigger processes like autophagy, where your cells clean out the old and damaged parts to function better. Then there's cold therapy. Exposing your body to low temperatures can activate proteins that protect cells and improve overall resilience. Supplements like resveratrol, NAD boosters, and metformin are also gaining traction for their potential to enhance cellular repair and energy production. But here's the thing. While these strategies seem promising, not everyone agrees on their effectiveness or who should have access to them. Critics argue that these breakthroughs might only benefit the wealthy, leaving others behind. And some question the ethics of investing so much into anti-aging research when global health challenges still exist. It's a debate that raises tough questions about fairness and priorities in science.
Opposed to a cell is to break its chromosome, because it's going to die if it doesn't fix it, or worse, for the body, you get a tumor. So the cell has to hunker down, stop dividing, arrest just about everything it's doing, and then try to repair that broken DNA. But in doing so, it has to do two things. First of all, it has to take proteins from somewhere else that are doing a good job keeping the cell from functioning, or making sure the cell's functioning correctly. And those proteins are used by the cell to repair the DNA that's broken. But also what's happening at the break is that that's all opening up as well, because you remember, if you break a DNA and it's spooled up, you can't fix it, you can't glue it back together unless you unpack it, stick it back together, and then you've got to repack it. So this movement of proteins and the unpacking, repacking of the DNA, I believe, leads to cells losing that original youthful, what we call a gene expression pattern of how the genes are turned on and off. And nerve cells, as they get older, lose their ability to stay nerve cells, and liver cells lose their identity as liver cells.
All right, so do proteins, the way that you're talking about them, sound like little creatures? I think of them, because of my background, like powder, like just sort of inert molecules, which clearly, judging by the way that you're talking about them, they're not. I've seen them animated before as having like articulatable shapes, and they actually move. Is that accurate?
Well, that's essentially it. It's super exciting when you realize that proteins aren't just blobs or powders in the cell. They're actually little machines, like Pac-Man, that go around and they...
Dr. David Sinclair isn't just an expert. He's living proof that his research works. Despite being in his 50s, he's often mistaken for someone decades younger. His work has inspired millions to rethink what's possible when it comes to aging. But what's truly exciting is where this research could lead. Imagine a future where age-related diseases like Alzheimer's and heart disease are things of the past. A future where living to 100 isn't just common, but healthy and active. Dr. Sinclair believes that by addressing the root causes of aging, we can not only extend life, but make those extra years worth living. And while we're still in the early stages, the progress being made offers a glimpse into a world where aging no longer limits us. The question is, are we ready for it?
Tiny pair of scissors, they clip off chemicals called acetyls. And in doing so, when they clip off the acetyls off those packaging proteins, the DNA gets more compact. And that's called gene silencing. And over time, as we get older and through this DNA damage process, the sirtuins get inactive, they're distracted by DNA repair, and the packaging of that DNA, that hose spooling, starts to loosen. And now genes that have no business being on in the brain come on, and partly I believe that's why we have these diseases of the brain.
Fuck, that's so interesting. Okay, so one, I want to know from a lifestyle perspective, what are we doing that's speeding that up? And then two, what can we do from a lifestyle perspective to begin slowing that down or reversing it?
Well, so I've been studying these enzymes, the sirtuins. We have 7 in our bodies. I've been studying them for about 25 years. The numbers of clinical trials in humans is that you want to pulse it, let the body recover, not constant. We used to make animals go hungry all their lives, and it worked, but it actually works better if you let them recover, and I think that's the secret.
Then let's really dive into that. So I'm guessing you're talking about where animals were denied something like 20 to 30% of their caloric intake for very long periods of time. It was extending their life by what, like 30% or something? So super interesting, but you're saying that if their caloric intake over a long period of time is roughly the same as an animal that's just allowed to eat until it's satiated, that if it's done in a pulse pattern of hunger and almost overfeed, they actually have the same benefits as the animal that has a chronic deficit of calories?
All right, well, let's be clear. Nobody knows what the perfect diet is, even when it comes to fasting. It's all largely based on rodent studies. So what I can tell you about the rodent studies, which I'm very familiar with, is that if you take a rodent and reduce its calories by 25% for its whole life, it will live longer, 30%, but it'll be really miserable and aggressive. And that's true for us as well. I've tried calorie restriction for about a week and I gave up. I was pretty angry. But what we discovered, my colleagues discovered, is that it's not just what you eat, it's when you eat that's important. And what's been found is that as long as you have that period of hunger in a mouse, so you can feed them every other day.
It became a pretty clear apex predator. It's not that things couldn't take us out, but I mean, by and large, obviously look at how far we've come. They didn't. So why would we only live to 40? Is it that whales continue to breed and be useful in that sense?
So that's really super interesting, and very few people talk about this. The reason is that we were not at the apex of the food chain until recently. But in a world where we typically would die from starvation or from war, a lot of men didn't make it to 40 because of that, we were at the middle of the food chain. Only now we barely have a chance of dying before 70 or 80 unless we're unlucky. Give us another 5 million years of evolution, we could evolve 200-year lifespans. That's what should happen if evolution continues. A whale has been at the apex for about 30 million years, and they've been allowed to evolve those long lifespans. We are just like them. We share most of their genes. They're warm-blooded. They produce milk. They're